pressure has been somewhat loosely defined as force divided by area. The formal definition that we're going to use here is that the pressure at a point is the differential force perpendicular to the surface divided by the differential area. That is, if we have a force acting on a small area, we have an approximation to the pressure. We take the component of the force perpendicular to the area and divide that, we get the approximate pressure. In the limit, as the area goes to zero, what we get is the pressure at the point. And that pressure can of course vary from point to point, and often does. So it's a limiting value of F perpendicular over the area as the area approaches zero. Again, F is a force perpendicular to the surface. We have the continuity equation, which says that when we have a flow of an incompressible fluid, at least, in a closed system, that the rate at which volume passes a point, the time rate at which volume of fluid passes a point, is equal to the cross-sectional area of the flow multiplied by the volume. Again, we can think of a pipe with cross-sectional area A and fluid flowing through at velocity v, and the rate at which volume passes is then the area times v, which is something we've covered in the general class. And this, of course, implies that, well, this is the rate at which volume flows. This is the flow rate, in other words. This flow rate is constant in an incompressible fluid in a closed system because the flow has no place to pass but through the system. So that, in this case, the product of area and velocity is the same at one point as at another. And this, of course, is the continuity equation, which we have talked about in class, so that's not really a topic that's specific. The thing that's specific is the definition of the flow rate as dV, the rate of change of volume over time. Okay, the volume flow over time, and the differential expression of that. Okay, the definition here is the definition of temperature. We've done this implicitly in class, but the definition we're going to use is that the ratio of two temperatures is the ratio of the two pressures if we have a closed system with a fixed amount of an ideal gas. That is, a constant volume with a constant amount of ideal gas. I should have N equals constant there. And of course your temperature here is measured in absolute terms. So again, in this situation, constant velocity, constant amount of gas, of an ideal gas, the temperature ratio will be the same as the pressure ratio.